evidence of entanglement between quarks and gluons has completely changed this picture. Instead of a static system, we are witnessing a much more complex and dynamic structure. Scientists, through experiments and particle accelerators at extremely high energies, an advanced method that allows them to observe inside the proton, the fundamental particle within the nucleus of all atoms. These experiments, thanks to powerful particle accelerators like the Large Hadron Collider, LHC, have revealed that quarks and gluons, the fundamental components that make up protons, not only interact simply but are also quantum entangled. This is the first time science has proven that these particles do not exist independently but have quantum connections, interacting closely with each other according to complex quantum laws. Entanglement is an aspect of quantum physics, suggesting that two affected particles can instantly influence each other's state, regardless of how far apart they are, even if they are on opposite sides of the universe. Albert Einstein built his theory of relativity based on the notion that nothing can travel faster than the speed of light. However, this would exclude the instantaneous nature of entanglement. As a result, Einstein was so puzzled by entanglement that he famously described it as spooky action at a distance. Yet, despite Einstein's skepticism about entanglement, this strange phenomenon has been verified time and again. Many of these verifications involve testing increasingly greater distances over which entanglement could be demonstrated. This new test took the opposite approach, investigating entanglement over distances as small as a trillionth of a meter, and discovered that it indeed occurs within individual protons. The research team found that the information sharing that defines entanglement occurs across each group of fundamental particles, called quarks and gluons inside a proton. According to team member, physicist Zhu Junbing II of Brookhaven Laboratory, in a statement, "Before we conducted this work, no one had ever examined entanglement inside protons in experimental high-energy collision data. For decades, we had the traditional view of protons as a collection of quarks and gluons, and we focused on understanding the so-called single particle properties, including how quarks and gluons are distributed inside protons. Now, with evidence showing that quarks and gluons are entangled, this picture has changed. We have a much more complex and dynamic system." The current research is the result of 6 years of work, helping scientists better understand how entanglement affects the structure of protons. When particles collide at extremely high speeds, other particles fly out of the collision like debris from a vehicle crash, creating a chaotic scene. Scientists use a technique developed since 2017, combining quantum information science with data from electron-proton collisions, to study the effects of quantum entanglement phenomena on the paths of particles produced after collisions. This technique is based on the principle that if quarks and gluons inside protons are entangled, it would be reflected in a level of chaos, or entropy, observed in the subparticle streams. To visualize, compare it to a room. A messy room, with clothes and items scattered everywhere, represents high entropy, a high level of chaos. Conversely, a neatly organized room, with everything arranged orderly, represents low entropy, a high level of order. In this context, the messiness of particles after collisions could be a sign of entanglement. Theoretical physicist Dimitri Karzai, from Brookhaven Laboratory explained, "For the maximum entanglement state of quarks and gluons, there exists a direct relationship that allows us to predict the entropy of particles produced in high-energy collisions. We have verified this relationship with experimental data." To determine the level of disorder of particles after collisions, the research team initially analyzed data from proton-proton collisions at the Large Hadron Collider. Then, to obtain cleaner, less noisy data, they switched to data from electron-proton collisions conducted at the Hera accelerator from 1992 to 2007. This valuable data was provided by the H1 group with support from the group's spokesperson. Researcher Stefan Schmidt from the DESY electron synchrotron, abbreviated as DESY, after 3 years of searching and processing results from Hera. The analysis of Hera data showed an astonishing match with theoretical entropy calculations. This match provides strong evidence that quarks and gluons inside protons are indeed in a state of maximum entanglement. Schmidt emphasized, entanglement doesn't only occur between two individual particles, it can exist among many particles. Maximum entanglement inside protons appears to be the result of strong interactions creating a large number of quark, anti-quark, and gluon pairs. Clarifying the maximum entanglement between quarks and gluons inside protons not only helps decode the force holding fundamental particles together, but also opens new insights into the nature of atomic nucleus building blocks. These discoveries have the potential to clarify how fundamental particles operate when influenced by their surroundings and interacting with other particles. Specifically, studying the detailed entanglement between quarks and gluons can provide crucial information about how the structure and properties of protons change when they are part of larger atomic nuclei. An important question arises as to whether the crowded nuclear environment, where a proton is surrounded by many other protons and neutrons, has a negative impact on this quantum entanglement or not? This process is called quantum decoherence, which can weaken or even break the inherent quantum linkage in individual protons. The physicist comments that, to answer this question, we need to conduct experiments with electrons not only on single protons but also on complex nuclei. In particular, using modern tools to study entanglement in a proton when it is within a nuclear environment will be very useful. This helps us better understand how the nuclear environment affects the quantum state of the proton. Such studies will be the focus of the upcoming electron-ion collider at Brookhaven National Laboratory. Expected to be operational by 2030. This machine will provide advanced tools to investigate in detail the interactions between electrons, protons, and nuclei, opening opportunities to explore previously unknown secrets in nuclear physics. Studying entanglement in a nuclear environment not only helps us better understand this complex quantum behavior, clarifying how particles maintain or lose coherence, but also expands the perspective on the connection between traditional nuclear physics and quantum phenomena. This will be a major breakthrough in the journey to decode the fundamental laws of nature. Thank you for watching today's video. Please subscribe to the Hidden_Realms channel to support us, and don't forget to subscribe to support the channel. Thank you for watching today's video.